Hey, what's going on, guys? Let's look at this problem right here. Here this question is asking, determine electron and hole concentration for silicon at T is equal to 300 degree Kelvin if the Fermi level is 0.22 electron volts above the valence band energy level. Okay, now let's look at this one through a diagram. Here they are asking us to find out the electron and holes concentration, and also they have given the location of Fermi level, that is above valence band energy level 0.22 electron volts. Now whenever we talk about valence band and conduction band, we will have two bands right here. The top one will be conduction band and the bottom part is valence band. And here they are saying we have a Fermi level that is 0.22 electron volts above the valence band. This is the valence band. The bottom part is the valence band. This is valence band and this is conduction band. And we have a Fermi level that is above 0.22 electron volts. 0.22 electron volts above the valence band. So this is EF that is given, and this is EV, and this is EC. Now here the location given is EF minus EV. Here we are interested in calculating the electron and hole concentration. Okay, this location, this distance is given 0.22 electron volts. Now we have to look at the equation that is connected to Fermi energy level and valence energy level, and also some hole concentration or electron concentration. The equation, if you look through the equations, you will get this one. KT EF minus EV is equal to KT ln NV over P naught. So this is the equation that is related to Fermi level energy band and valence energy band. Okay, now we have this one. From this one we can calculate the hole concentration, because P naught is the hole's concentration. So we can, if we solve for this equation, we can calculate that one. Now let's look at the available informations. K is Boltzmann constant, we know that one. T is the temperature, we know that one too. And then NV is the standard value for every different semiconductors. So if you have silicon and 300 degree Kelvin, it's going to have a particular value. Usually in the question they will give that value, so we don't have to worry about that one. So that's going to be like a NV for silicon at 300 degree Kelvin. That's going to be equivalent to 1.04 times 10 to the power of 19. So you have to remember every semiconductor has different value at 300 degree Kelvin, right? If they ask for silicon, this is the value. So we have silicon, since we have the silicon, this is the value we are going to use. Now we have this one, we can calculate the concentration, right? The hole's concentration. In other words, we can say KT ln, instead of P naught, we can put Na. Both are same, acceptors, right? So we have to just rearrange this equation and plug the values. Now we know that 0.22 electron volts is K times T. K is 300. K is Boltzmann constant. Boltzmann constant is 8.62 times 10 to the power of minus 5. The temperature is 300 ln, and the value given for NV for silicon at 300 degrees Celsius, that is 300 degree Kelvin, is 1.04 times 10 to the power of 19. And we are interested in calculating the hole's concentration, that is Na. Okay, now let's go ahead and rearrange this equation. So we can bring this. If we take ln both sides, we will get some value. Okay, let's move this. If you simplify this 8.62 times 10 to the power of minus 5 times 300, you are going to get 0.0259. And here we have 0.22. And here we can move these two to one side. Okay. And also we have this one multiplied by ln of 1.04 times 10 to the power of 19 over Na. Okay, now to get rid of the ln, we have to take e both sides. Like we can take e power both sides, but before we do that, we have to move this one to this side. Let's continue this one over here. Okay, if I move this one, this is going to be what, 0.22 divided by 0.0259. That's going to be equal to this ln of this value. So if I take e power, this ln and e power cancels each other, and we will get 1.04 times 10 to the power of 19 divided by Na. And if you calculate this e power value, you will get 4914.77. that is equal to 1.04 times 10 to the power of 19 divided by Na. Therefore, if you rearrange this Na and solve for Na, you are going to get 2.12 times 10 to the power of 15 per centimeter cube. So this is our Hol's concentration. Now we are not, Hol's concentration is not the only question, right? We have to find out electron concentration also. So to find that one, we can use the mass action law. Mass action law says that Np is equal to Ni square. Okay, so let's get rid of this one. Okay, we found out this first part. Okay, this is the first answer, that is Hol's concentration. Now we are interested in finding the electron concentration. Mass action law says that NO, like number of electrons times number of holes, is equal to Ni square, right? So this is the equation we have. Now here we are interested in finding the electron concentration, because we already have P naught, that is Hol's concentration, that's available right here. So let's go ahead and rearrange this equation in terms of electron concentration. So this is going to be what? Ni square divided by P naught. So let's get rid of this one. Okay, Ni square divided by P naught, and Ni square is intrinsic value, like intrinsic concentration of Si at 300 degrees Celsius. That one is always, this is a predetermined value. This is going to be given in the question usually. 1.5 times 10 to the power of 10 divided by P naught, that's what we calculated before. This is going to be 2.12 times 10 to the power of 15, and if you calculate this one, you are going to get 1.02 times 10 to the power of 5 per centimeter cube. So this is going to be our electron concentration. So we calculated the Hol's concentration. This is Hol's concentration and this is electron concentration, right? That's the question is asking for. Now if they ask what type of semiconductor this is, you can look at this one, like you can compare the values. If you look at the Hol's concentration value, that's comparatively much more bigger than electron concentration value, because this is 10 to the power of 15 and here we have 10 to the power of 5. So this is going to be the larger, this is going to be the majority impurities, right? So this is going to be the majority. So if the holes are majority, we are going to have p-type semiconductor. So this is going to be p-type semiconductor. So that's going to be the final answer. Like we just the question is just asking for the electron and hole concentration, and that's all we need. That's how we do this kind of problems. I hope this helps. Thanks for watching.